In this course, we've gone back and forth between developing a language, the first order logic, and then we would study the logic of the language that we had developed. So we've gone back and forth between making the language more complex and then studying the logic that we get with that language. So we're at the final stage now where we're going to study the logic of the first order logic language that we have developed, which now includes the universal and existential quantifiers. And in this case, we're going to actually be looking at how to do proofs that use the quantifiers. So I'm going to go over in this lecture two of the easier steps that we can use. You'll notice that they, as I've sort of put them up here, they are elimination and intro rules, but we'll have to, again, be careful with the words elimination or introduction because they can, in some cases, be misnomers. So in this little video lecture, we're going to talk about universal elimination and existential introduction. So let's start with the universal elimination. The idea behind universal elimination is that you have some sentence that starts with a universal quantifier, and then there are going to be some instances of x, right? So of some of the variable x. And as the name in this case suggests, the idea behind the elimination is that you can plug in a specific name for all the instances of x. So say this sentence said, everything is a cube. Well, from there, you're allowed to infer that A is a cube. And if it also turns out that there's an object called D, then you would also be able to replace the X with D. So both cube A as well as cube D will be valid inferences that you can make from the universally quantified sentence. So the basic idea here is pretty simple. For all the instances of X, you can replace it with the names of objects that exist in the domain. That includes if this sentence is in fact some type of conditional. So suppose we have something like, if x is a cube, then, separate this out, then large x. As long as the x that is being bound by this quantifier out here, I replace all the instances of x inside the scope of that quantifier with some object, with the name of some object in the domain. So in this case, if I had the universal quantified sentence, for all x, if x is a cube, then x is large, I can then write out, and let's say b is the name of an object in our domain, then I can write out this sentence. If b is a cube, then b is large. Now notice, if b turns out to be a dodecahedron, this sentence is still true. And the reason for that is because, maybe most succinctly, we can think of this conditional as being equivalent to the negation of the antecedent and the consequent, right? This sentence would be equivalent to not cube b or large b, right? So even if b is not a cube, let's say it's a dodecahedron, then this sentence would still be true of it, because either b is not a cube or b is large. Okay, so that's doing universal elimination. Let me just delete this part. So again, if you've got a universal quantified sentence, you can replace all the instances of the variable x with a name of an object that exists in the domain. Now let's turn to existential introduction. Existential introduction sort of works in the reverse of universal elimination. You start with a claim, say that B satisfies some predicate S. You're then allowed to infer, well, since B is an S, we can introduce the idea that there just exists something that satisfies being an S. We sometimes call this existential generalization as well, right? You're sort of abstracting away the fact that it's B that satisfies being an S, and you're just saying, hey, look, there's something that satisfies being an S. So for example, if I had the claim that B is a cube, then I would be allowed to infer that there exists an X such that X is a cube. So here we're going from a particular case to a general case, but notice the generalization is to the existential. We're not moving to the universal introduction, right? And this makes, I think, intuitive sense, right? If you know that B is a cube, well, then you know there is at least one thing that is a cube. Okay, so those are the two basic ideas behind the universal elimination and existential introduction. Let me give you also an example. Okay, so what I've done here with this example is started with, there are three premises here. Let me put this here. The first one says that all cubes are large. Right? So for all x, if x is a cube, then it's large. Second premise says that all large things are going to be left of B. I think that is what I wanted. Yes, that is correct. And then the third premise says that D is a cube. The conclusion here, the goal, is to claim that there exists an object that is large and left of B. So here's how we're going to use the two types of rules that we have. Right? So we've got universal elimination and existential introduction. You're going to see me use this in Fitch in a little bit, but right now I'm just showing you how we can do this just on a sheet of paper, right, or just some other Word document, or in this case, Pages. So my goal is to say that there exists an X that is large and that is left of B, right? Presumably, that object is D, right? That since D is a cube, then we know by the first premise that D is going to be large, because one says everything that's a cube is large. And then premise two says that everything that is large is left of B. So then we know that D is going to be left of B. And since D is left of B, we know that there is something that is large and left of B. So here's how we're going to apply the two methods, the proof steps that we have so far. So in the first case, what we're going to do is take the first premise, there exists, for all x, if x is a cube, then x is large, and we're going to replace the instances of x with D. So it'll be cube D, then, then large D. My justification for this is the universal elimination, and that will be citing line 1. So in Fitch, you're going to see introduction and elimination rules, right, for the two quantifiers, and so that's what you would use. Now I can get this intermediary step, right? So if you remember for what we called modus ponens, or material conditional elimination, right? I can now actually write down large D. And the reason I can do that is because I have the antecedent from premise 3, and then I have the rule which says, well, anytime I have a conditional and the antecedent of that, I can infer what the consequent is. So this would be using conditional elim from lines 1 and 3. Okay, you're going to see in a moment why that's sort of important. Okay, again, using the universal elimination, I can also write down that if D is large, then D is left of B. And that's coming from the second sentence, right? What I've done here is replaced all the instances of X with D down here. So just as we used universal elimination for this line up here, right? Now I can use that from number 2. And now what I can do is, since I have from line 5 the claim that D is large, I can also write down that D is left of B using, again, the conditional elimination. So I can write down left of DB. And that, again, is from conditional elimination. Citing lines, this is now going to be 5 and 6. Maybe I should put some numbers here just so we know what we're talking about. This is going to be line 5. This is line 6. This is line 7 now. And I'm just using this dash to signal the horizontal Fitch bar that you would see in a Fitch style proof, which I'm sort of modeling this after. I just don't have the vertical lines at the moment, but that should be okay since we don't have any subproofs. And let me just delete that just so we have it clear that I'm not skipping any or having empty lines. Okay, so now I've got the claim that D is large. I've also got the claim that D is left of B. If I look at my goal, I can see that I have this conjunction. Here I'm using the ampersand notation for expressing conjunction. So I can combine 5 and 7 together, and I can say that D is large and that D is left of B. This is going to be conjunction introduction using lines 5 and line 7. So the justification for 5, 7, and 8 are using rules that we've learned in the past. Now that I have the form of this sentence, so you should see the similarity between 8 and the goal is just that in the goal, I've replaced D with a variable X, because now I'm not saying it specifically that D is large and left of B, but there's just some object that is large and left of D. And so I'm going to use now the rule existential introduction to justify that step. So I'm now going to replace the instances of D in these 2 spots with the variable X. And I'm going to put out front, I should make sure this is actually well-formed sentence, I'm going to put up front the existential claim. All right, so I've replaced D here and this D here with X's, and I've put parentheses to the left and to the right so that the scope of this existential quantifier is this entire formula right here. And so both instances of this X and that X are being bound by that quantifier up front. If I leave that parentheses out, then that won't be a valid inference step, right? This existential quantifier up front will only be binding this instance of X, and now this is actually a conjunction. The conjunction ends up being the main connective. But that's not what we want. We want to make sure to put parentheses at the beginning and afterwards to indicate that this sentence is actually not a conjunction. It's an existentially quantified sentence. So at step 9 then, I would have as my justification the existential quantifier, and this would be an intro rule, and I would be citing line 8. Okay, so that's an example that illustrates how we use both universal elimination and existential introduction in our proofs.